So today's speaker is Director Paola Caselli now. So Paola is one of the directors of the Max Planck Institute for Extraterrestrial Physics in Munich. And she's also visiting professor at Leeds and University of Florida at Gainesville, Ludwig Maximilians Universität in Munich.
A little louder.
Sure thing. And she studied physics and astronomy at the University of Bologna, and in her PhD she worked at Ohio State University with Eric Herbst, and also here with Phil Myers. And she's been a researcher at the Osservatorio Astrofisica de Arcetri with, thank you, with Galileo, along with Galileo, right? And she was
He was her assistant.
visiting scientist at UC Berkeley, yeah, right, and lecturer in the Department of Astronomy here at Harvard University, where she did her best work with me. That's about wraps it up. So
that's a bit biased,
and,
but yeah.
she's going to talk about astrochemistry at the dawn of star and planet formation.
Right, okay. Thank you very much, Eric. So it's a great pleasure to be here. I'm actually just so excited to see all of you guys. I mean, it feels really like coming back home and, giving this talk to my family. So I'm even more kind of nervous as I should be. So I apologize if sometimes I just say something and just ask questions if something doesn't make sense. So anyway, so I will, today I will just go through some of the important steps toward the formation, say, of stars and planets, following these through the astrochemistry tale. And we will see that actually it is very important, one stage in this star and planet formation process that is this starless course. As we will see, there are many of the processes that we then give, results and, for example, produce molecules that we will also see them later on in these other phases. So these are the various steps. We start, of course, with clouds, interstellar medium material that then contracts and forms some dense regions, and these dense region fragments form dense cores, and you have then the formation in some of these dense cores, the formation of protostars that then evacuate the cloud, and then you see these beautiful disks. And here, of course, you can follow these various stages, and even nowadays in our solar system, where we see and we can measure primitive material that is within rocks, like carbonaceous chondrites. So the question is there actually any link between this phase and the later stages? So I will try to show you that actually, yes, we think there are some links. And so let's move on, and I want to give you a little bit more motivation. So we know now about 200 molecules, and without considering isotopologues. So these are the majority of the molecules that are known and seen in space are organic in nature. So the greenish molecules here are organic in nature. And some of them are actually important building blocks that then can form even more complex organics, like prebiotic molecules, like, for example, the amino acetonitrile that was discovered in 2008 by Arnaud Belloche and collaborators. This is just a step away from glycine, the simplest amino acid. And of course, if we look at the primitive material in our solar system, we see in some of these meteorites, so in particular some of the most primitive carbonaceous chondrites, a lot of basically the building blocks of life. So we have not even just the 20 amino acids that we use in life, but we have hundreds of them. You can choose anything you want, and then you have not just that, you have fatty acids, you have nucleobases, basically everything you need to build a living being. Then, of course, the question is how you do that. That is a big question that many people are still working on. Good. Okay, so the outline, so I will just go through some, say, historical views to do an introduction about molecular clouds and dense cores. Then I will move into these important processes that are like the freeze out and the deuterium fraction. That, by the way, it's important also because also in our Earth, as you know, our oceans are deuterated in a sense. The water, there is a ratio between heavy water and water that is 10 times larger than the D/H cosmic abundance. Talk about the water and the prestellar core dynamics, and then some complex organic molecules in various phases. And then, if I have the time, I'll show you some of the recent work that we have been doing on the early phases of protoplanetary disk. So let's get moving. Our galaxy, so I think I don't need to explain much here, except for the fact that where you see these dark lanes, that are those where cold material, in particular gas and dust, with temperatures, say, below 100 Kelvin, they basically don't shine at all if you look them in the optical. But, as we know, since many years now, they shine in molecules. And you see these molecules, these organic molecules, basically everywhere. Of course, CO is the most abundant of them. And then, in fact, the CO is not, say, the best tracer of the dense regions where the stars are forming. Like you need to go to rarer isotopologues, and now you start to see some correlation between the young stellar objects that are in colors and the dark regions here that are the filaments in 13CO. If you want to just focus on the filaments, then you have to go even deeper in, and then you need to use even rarer isotopologues like C18O. And now you start to kind of identify sometimes the so-called dense cores. This is work led by Phil Myers and collaborated this very important paper in 1989, where it showed very important properties of these regions where actually stars, these are the basic units of star formation. But you don't see them very well in CO. You see them in molecules like ammonia, you see them in molecules that actually requires a bit higher density than what is required for the CO line to be excited. And for example, this is work that I did when I was here and then published a bit later. It was on the N2H+. This is a great tracer of dense gas. And by dense, I mean anything that is between a few times 10 to the 4 to 10 to the 6 per cubic centimeter, H2 molecules per cubic centimeter. So with Eric, we then look into this a little bit deeper and realize that actually there seems to be some kind of two classes of these dense cores. So we are talking about now dense cores that have not yet a star yet. I'm interested in understanding how stars form, so I want to know the initial conditions. So on the sky in our galaxy, these nearby cores that you can measure very much in detail, you can look at their density profiles. You can look at the abundance of CO, which is here. So this is in log CO, is the red. This is the transmission, so it's e to the minus visual extinction, and the log density. So this is in the blue. So you start to see striking differences between different cores. In this particular case, it's B68 and L1544. What is the main difference here? The main difference is that cores like 1544 are highly centrally concentrated. They have very spiky type of density profile, and you also have a very sharp CO freeze out. So CO disappears, and I will show you in a minute. So these things, what happened here is that we have also line profile molecules that, of course, are unique tracers of dynamics that can tell us that in this case here, for example, this is work that was led by Charlie Lada here, showing that these line profiles are consistent with oscillation. In this case here, we have actually profiles consistent with the contraction motions. And we call these, or say I call these, so from now on, I call these prestellar cores. Why? Because these are the cores that are going to form stars, because they are, say, out of equilibrium. They are contracting. We see that there is inward motion, so it's very hard to, say, believe that they will not form a star. So let me just give you now, switch into the chemistry a little bit more. So this is the millimeter dust continuum emission from this prestellar core that we have been studying very much because it's very nearby, it's bright. And as you can imagine, this prestellar core don't have a very long life because they are short-lived. These are going to form stars relatively soon. So then what it means is that you're not going to find them many around, okay? So it means that if you find one, look at that and just try to understand what's going on as much as you can, and then try to find some others. Anyway, so this is the dust peak that you see. So again, long time ago, we did this measurement of the C17O, showing that there is a nice hole in the CO in correspondence of the dust peak. Remember that this is a optically thin isotopologue, and you can even measure the optical depth because it has hyperfine components. So the best way, or say the simplest way to understand this, is that you have CO molecules freezing out onto the surface of dust grains. How much of this? Well, actually, if you use CO as a tracer of mass, well, you are actually in error here because you lose about 2.3 solar masses out of the total solar mass of the whole core here, which is about 8 solar masses. So for the central region, definitely CO is not good. Of course, I should quote here earlier work done by Willacy and also work by Ted Berlin on B68. So in these cases, these are less centrally concentrated objects, so that it's not as extreme as this. Now, once you have CO freeze out, you then need to find a molecule that is good in tracing the central region. So that was our job more than 10 years ago. And we actually found that the deuterated molecules are very good tracers of regions where CO is frozen out. We kind of knew that because there was a theory that I will show you that told us actually in the 80s that was the case. So this is again the submillimeter continuum emission. This is the N2H plus in color. This is the N2D plus in color. You start to see the shift in the peaks. N2H plus is not actually peaking toward the dust peak. There is already, you start to see some freeze out of the N2H plus here, but N2D plus is peaking. And the fraction of this deuteration is 20%. And you have to compare this with the 1.5 times 10 to the minus 5, which is the D over H cosmic abundance. There have been many, here I'm not even quoting all, but many papers measuring deuterium fractions, and you can see that some numbers go really high, close to unity. I just put these in yellow, not just because Silvia Spezzano is in my group now, and she's doing a great job, but also because there are some people from the audience here, like Mike McCartney, who actually helped us with these studies. So this was the discovery of the doubly deuterated C3D2 and the measurement of the deuteration. It's not just this little core that has this high deuteration and CO freeze out. We see this everywhere we look at. Of course, you have to choose a region that is relatively quiescent. You don't want to go nearby a massive star because then, of course, you have feedback, you have heating, and you're not going to find the initial conditions. You have triggered conditions, but that is not what we are interested. So here, for example, an infrared dark cloud, these are these very dense clouds that are seen say so they are opaque in the infrared, that's why they're called the infrared dark clouds. And what you see here is the map of the N2D plus. So we have the N2D plus, actually all around this map is quite extended. And also the CO is depleted. Here we get up to depletion factors of 5, which means that, say, about 85% of the CO is on the surface of the grains. The thing here that I wanted to show is just there are many now studies that have been done. So it seems that it's a quite universal, at least say in our galaxy, universal factor that you have this freeze out of molecules and then this activation of the deuteration. How does it go? Well, this is, I think, the main reaction. You see, this goes back to the 70s by Watson, who studied this process. And pointed out that this reaction is exothermic. So in cold gas, this reaction cannot proceed from right to left. And then there was Dalgarno and Lepp, who in '84, with a very short paper, they explain very well that actually if neutrals, for any reason, they didn't even mention, say, freeze out, if for any reason these, say, neutrals like CO and N2 and oxygen that destroy these ions are gone, you have an increase in this ratio. And the reason is that you have lower destruction rates on one side for both of these ions, and also higher formation rate, just because these proceed faster because you have more H3+. So at the end, you have the larger D over H. And these, of course, can move on, not just to H2D+, but also D to H+, etc. And in fact, this is what we saw. I mean, a very bright H2D+ ortho line. This was back in 2003. And this was in one of these prestellar cores. So it was very well matched with the theory, although at that time, the theory, say the chemical theory, was not very good because we couldn't predict these when we did these observations, I mean, in our proposal. But anyway, this was great because we could actually trigger great people to do new laboratory work, to do theory on this ion, and this is the work that we are still doing at the moment. There is a little trick about the deuterium fraction, but actually the trick is kind of good for us because we can learn how to use this for measuring ages of clouds. That has been a kind of difficult problem, and it probably still is because there are, of course, observational difficulties, etc. But I think we are getting close to this. So what it is, I'll try to explain briefly here. So we have the H2 molecule that has two forms, has the para and the ortho. This is depends on the orientation of the spins. And the para has a ground state at 0 level, and then the ortho has the ground state at much higher energy. Now, depending on what is the collisional partner for this reaction here, so for to go back, say, to the H3 plus and HD, if you have ortho H2 that is more energetic, it will overcome more easily this activation energy, and it will basically drive the reaction backward and reduce the deuterium fraction. So it's very important to understand what is the ortho to para H2. It's not just that you want to know the temperature, the density, to understand the chemistry. You also need this ratio, and this ratio is terribly hard to measure because you see here these energies. There is no way that we're going to see these lines in cold gas. The other curve here is the deuterium fraction. So you see that as you move down in this curve, there is a mirror curve that is the deuterium fraction that goes up and reaches the values that are typically observed. So you really, we have to have this plateau here. We have to arrive at this plateau here to, say, reproduce what is seen in some of these objects. So we talk about, you see, million years, and that is for this dense gas, sometimes this means that you are looking at objects that are probably standing there since about 1 million years, which is about sometimes 10 times the free fall time or dynamical time, because we are talking about the densities of the order 10 to the 4th and to the 5, and even more. So anyway, I here very quickly just to say two things. So one is that the chemistry of these ions is actually very simple, and it has been tested, and at the end you can reduce the system to very few expressions. And the other thing that I want to say here is that, okay, you cannot measure ortho to para H2, but you can measure the ortho to para H2D+, and these two things are, can be connected with the coefficients that are just the rate coefficients of this reaction, with plus and minus just meaning forward and backward. And then you can actually, if you measure these, you can understand these, and you can have a understanding of this time scale. One thing that I didn't say here is that why do we start with 3 here? Well, the starting of 3 here is the starting point when molecules are formed on dust grains, and we think that the H2 we'll just take off the statistical ratio, which is 3:1. Okay? Okay, so then we did that. We have the ortho H2D plus that can be observed with APEX, for example. Back 10 years ago was the CSO that we used. And now, unfortunately, Herschel was not able to detect the line, the 1.37 terahertz line of para H2D plus, but with SOFIA we were able to do it along the line of sight of a very young protostar, so a region where you have still a lot of cold envelope, so you are probing the cold material along the line of sight. And in this case we got, so comparing these two, and of course with our chemical models and staying as conservative as possible, we found, say, age estimates of about 10 times the free fall time. So a region that must, in a sense, have some support, of extra support, otherwise it was supposed to collapse, say, toward the center and for the star. These are the lines I have been talking about, just in case you're interested in trying to detect them. So I just say that the para H2D plus and the ortho D2H plus can only be observed with SOFIA. So the para D2H plus, I should say, also quote the work done by Berenger Paris in 2011, where she detected it in a core in Ophiuchus. And now we have also, this is the first detection of ortho D2H plus with SOFIA that was done not long ago, and Jorma Harju is leading this work. You see this beautiful absorption line again, and you also have interesting shape of the line, so you can actually learn about the kinematics of this envelope, and so there is all the modeling going on, but I don't want to bother you with this now. So deuterated molecules are a great species to say, measure the motions and the properties of the central region of these cores. Here, for example, I have the work done by Antonio Crapsi in 2007, where we have some interferometric data. The color is interferometric ammonia, and here is interferometric deuterated ammonia. This dashed circle here is the same as this one. This is just a zoom in, and this is the 90% contour of the dust continuum emission at 1.3 millimeter. So you see that the deuterated molecule just peak there, and you can also learn, of course, with the kinematics, so you can learn about velocity gradients, so you can learn about specific angular momentum, and this is one thing that we found, that going from scales of a fraction of a parsec, say 0.1 parsec of the core, that is traced by the ammonia down to, say, 2,000 astronomical units, you have a drop in the angular momentum towards small scale by a factor of more than 10, which is actually consistent with the models, say, theories of magnetic braking when you have a rotating and collapsing cloud. I come now to water because, interestingly enough, I mean, water that we at the beginning, we didn't think that this was something that could give us information about the central region of prestellar core. Why? Well, because water should be completely frozen out, and this was at least the prediction of the models. But actually with Herschel, thanks to Herschel, this was work within the WISH team. So this is the water in star-forming regions with Herschel that was led by Evin van de Soek. We were able to get this beautiful line that, okay, now is, you don't even see the scale. But anyway, so this is actually quite faint. We are in the millikelvin regime here, 2 millikelvin of, say, noise, and the line is not so bright, but the important thing is that we have this inverse P Cygni profile, and that helped us a lot to actually understand how much water we have and also understand the dynamics. What we got from this was like, of course, this gravitational infall, and that has to be within the central 1000 AU, because water, you can excite it only at high densities. So densities like 10 to the 6 or more. and you only have those in the center. And you see the emission here. This is the blue part that comes towards you, that is in the classical example of infall motions. The total mass of water vapor that we have within the beam of Herschel is 0.5 Earth masses. And then, if you wanted to reproduce this with your chemical model, well, this means that you have to have at least, say, between 2 and 3 Jupiter masses of water. So you have a lot of water ice already there, and this water ice is contracting toward the center, so whatever will form there, so the future stellar system will have, say, already quite a lot of water to, say, play with. And one thing we also pointed out is that we really need this cosmic rays here, because without cosmic rays, there is no way you get this water back into the gas phase. So that was another important point. So now it comes with Eric. He led this very nice work on the dynamics, because you see, when we look at different predictions from a theory of how cores should, say, contract and form a star, so the infall and the contraction of dense cores, well, if you look at the density profile of what they predict, say in their density profile, well, you don't see much variation. It's very hard to actually observationally disentangle between these various profiles. This is the singular isothermal sphere, the Larsen-Penstone, and this is the quasi-equilibrium Bono-Reber sphere that is best matching the data that we have from this L1544. However, if you look at the velocity profile, they look very different. So now that we have all this information about the kinematics, and not just the water, but also other lines, so why don't we use these to actually put some constraints? By the way, this quasi-equilibrium, you have to consider this Bono-Reber sphere that is contracting very slowly. And in fact, I mean, if we get well, I'll show you here, if you just let it go and contract at a higher velocity, you are completely off in reproducing the water profile, but not just the water, also the CO profile. Okay, so CO, this is the C18O. You can see, for example, the Larsen-Penstone, you have these 2 fissures, just because in the outer envelope you have large velocities, so you see the back and the front of the cloud, so, and you have the depletion in the center, and in any case this doesn't work. So this was a very good match, and we could make some constraints, say, on the dynamics. And in fact, this is an overall view of this region. So we have been studying this since many years. As I said, the lines are bright, so we can study in detail the dynamics and also the chemistry. And you can put these in slabs with different extinction, going from the outer part to the inner region, where the extinction actually goes as high as almost 100 magnitude toward the very center. So it's really dark and cold, because in fact I didn't point it out, but the temperature that we get from the ammonia VLA data within the 2000 AU is 6 Kelvin. So the other thing here that I have is the density profile of this, say, Bono-Reber sphere that appears to well match the observations, and I think even more importantly is the velocity infall profile that show this curve due to the fact that you have the infall increasing toward the center, but then around the 1000 it drops down because you have this thermally supported central region. Now, this region here is the thing that now I really wanted to study. And we have been getting data with ALMA. We are still analyzing, and I will show you a little bit what we have. And this is what we have. So this is the dust continuum emission seen with ALMA in this core that I have shown you before, the single dish data. So it's, first of all, I was very excited to see it because it's very difficult to get the continuum with these starless cores with an interferometer, because you have this larger cloud that basically you have most of the flux that is filtered out. But here, actually, we see we are left over only 0.3 solar masses out of these 8 solar masses. But you see it, and we see also some hint of substructure toward the center, which is also very, very interesting. This is 1000 AU bar. And this is the combined ACA and the main array, of course, for the ALMA. Then we come to the lines. So this is the curve here. The contours are, again, the continuum. And this is DCO plus 322 that shows this beautiful ring. So again, telling us something that we already knew, or that CO is almost gone toward the center, because you need CO to form DCO plus. Although, of course, it's a deuterated molecule, so it should peak toward the center. But if you don't have CO, you're not going to make it. And 2D plus instead is actually it's quite extended, so it doesn't show this sharper peak, say toward the center, but it is tracing here, and we see some interesting kinematics that we're still, say, working on, and Jaime Pineda is helping with this a lot. There is also some theoretical effort going on in the group. So this is Zhao, who has been working on formation of protoplanetary disk. This is an example of a core that, say, starts with similar properties as the L1544. What we have done now here is to use non-ideal MHD with the inclusion of very simple chemistry. So at least we wanted to, say, follow as correctly as possible the ionization fraction that, of course, in a magnetized cloud, it's very important. So here, because of some turbulence that is within the region, and the contraction and the magnetic field twisting, etc., in fact, you predict that you have some substructure, and this is, again, work in progress. So I cannot give you much more, say, information. However, let me move on from these early phases to a little bit later stages, which are the protostellar objects. So once you are in this protostar switches on, what happens? Well, first of all, you have higher temperature toward the center. So you have basically, you are heating up all the material that was moving toward the center, and with temperature, maybe of around 610 Kelvin. And rich in ice, you have all this thick icy mantle around the dust grain. And here, when the temperatures start to get above, say, 30 Kelvin or so, you start to release the volatile molecule, and then at 100 Kelvin, you release basically most of the material. So it's actually a good place to look at the ice composition, in a sense, if you catch the star early enough in its life, protostar early enough in its life. So what do we see actually here? So if we have, if we look at, for example, the deuterated molecules, what we notice is that, for example, looking at water, I can point out, say, ammonia, okay, well, formaldehyde, methanol, we don't need to go into all these other details, but the main thing that was striking for us is that, well, first of all, you have a lot of deuteration of methanol. People see triply deuterated methanol with very large abundances, and you can see the this is the triply deuterated bar. It gets quite large in fraction, and it means that you really need to enrich say the methanol by orders and orders of magnitude compared to the D over H. So here we really talk about more than 10 orders of magnitude. You have to have a super deuteration. This is what Cecilia Ceccarelli, in fact, coined this in, not in 98, a bit later, but the super deuteration of methanol. And on the other hand, for example, water can also be deuterated, but we do not see these excesses, say, of deuteration of water. So there is a little bit of difference between the two. And what we think is going on, and now we think at least this part is relatively well understood, is that we believe that, and this is actually consistent with the models that take into account the ice formation and the chemistry, and we just look here at the ice formation time. Okay, so basically the water formed first, and then we have these other molecules forming later. I have an extra slide to explain more my point. I hope this is more clear. So what happened is that when you look, for example, at background star along the line of sight of molecular cloud, so you look at the background star, you look at the spectrum of the star, you see absorption fissures. And some of these absorption fissures, if you look at the extinctions that are not very large, you see mostly water, okay? Then if you move toward denser region, so basically this means in history of the cloud or the dense core, you start to see also other molecules, and what we thing is going on is that once you go in a region of the cloud where the carbon is mostly in CO form and start to freeze out, you have lots of CO molecules, say, on the surface, and they can also start to hydrogenate and deuterate. And of course, toward the center, where you have this large freeze out and the large deuteration that goes together, you can actually deuterate a lot the outer layer and make all this deuterated methanol that then come off close to the protostar. There is also deuteration, of course, in disks, and now, I mean, with Karen here, she showed me some beautiful new example. This is a bit older figure coming from Matthews et al. That shows the deuterated molecule, the DCO plus, the 524, in the Herbig star HD 163296, showing again larger deuterium fractions, and we know much more, and more molecules in other regions. I think many more disks are coming up. So if I put these things together in a graph, this is what we did in our PP6 work with Cecilia and also people working in a solar system. If we put together the D-average in water and the D-average in organics in various environments, so going from pre-stellar cores down to Earth, basically, we see that this dichotomy, this difference between, say, water and the amount of deuteration in water in organics is persistent through many of these objects. Now, the other thing you notice is that there are not many data points here, so that is one work that we have to do, try to fill more these. But, for example, these are the comets. There is only one point here. I am desperately waiting for this Rosetta data for the deuterated molecules, so probably we will have another point, but we need more points here. So we have organic always higher. And again, if you remember, you can easily do this if you can trap what you're done in the pre-stellar phase. You can trap these ices and actually deliver it in the later stages in some way. Okay? Now there is also this nice, very nice work by Ilse Cleaves here in 2014 that also give us a message that is similar to what I just said, so that basically to reproduce the D/H ratio in our solar system, you really need to bring in some of the ices that are made during the earlier phases. Otherwise, it's very hard to increase this D/H ratio. Okay, so going to the complex organic molecules, again, we start from this pre-stellar cores, because this is where these complex organics appear to be, at least start to be made, as we will see. So before doing that, so here in this picture I just show a bunch of molecules, and in particular this recent paper by, again, Beloche, this very productive group in Bonn, that they work on detection of complex organics in high mass star forming regions. This is the Sagittarius A region, and they recently found this branched, so kind of bent structure of molecules that are very interesting, especially because amino acids also have this structure here. So apparently you can make these branched molecules already in this harsh environment in high mass star forming regions. So with Itascon, Jimenez Serra in 2014, she did this kind of radiative transfer exercise to see if, for example, pre-stellar core could be useful also to look for some of these large molecules and with prebiotic interest, like the simplest amino acid, which is glycine. Now, the reason to do that, I mean, if we could do that, that'd be great, because, of course, the pre-stellar core being cold and having very narrow lines, you can identify the lines much better, and you don't have much confusion, because if you look at these massive star-forming regions, you have broad lines, you have everything you can have, and it's very hard to identify. So, for example, here there is a spectrum, or simulated spectrum of a massive star-forming region, like a hot core type of region, where you have temperatures about 100 or 200 Kelvin, and you see that the glycine, yes, could be much stronger than what you expect in a pre-stellar core, but lots of lines here where also they will be blended with many more, say, simple molecules that are much more abundant. While for the pre-stellar core, you expect to have actually stronger lines toward lower frequencies in regions that, in fact, I mean, maybe with ALMA band 2, we could try to detect. So Hisaskun, she started a very deep, say, observations in these regions. So far, she did not detect the glycine, but she detected many other molecules. So here is a result from, again, this Protostellar core laboratory, which is L1544. And we have here two positions. So toward the cloud center, so toward the dust peak, and here is an offset position is where actually we found the methanol peaking. So it's like a region about 3,000-4,000 astronomical units outside. So what she found is that in general, although from this figure here is not so clear, you have to, of course, look at the abundances, so compare also with the column density of H2 that you get with the Herschel data. But what she found is that the abundance of oxygen-bearing molecules, and some of them are, say, organic, say, complex organic molecules, are much more abundant toward this methanol peak in this shell of the cloud, while others, and in particular the nitrogen-bearing molecules, are peaking toward the center. So now, of course, we need to understand why this is the case. So we have some models that have been run by Anton Baziunin that actually shows this peak. So this is the radius, and this is the abundance with respect to total hydrogen, that the molecules that have been detected, in fact, are predicted to peak toward the center, for the simple reason that toward this shell at about 0.01 parsecs, a few thousand AU away, because toward the center the density is really too large, and you just have, even if you produce these molecules, they can't stay in the gas phase for very long. And so this is a combination of surface chemistry, and more importantly, I think in the recent years is also, say, some gas phase chemistry that apparently is very important. So you still need, of course, the dust to form some of the precursor molecules, but for example, for some of the molecules, like in this case, like methylformate and also formamide, etc., it seems that also gas phase chemistry is quite important. And this was pointed out several years ago, but I think this paper shows it very clearly. This is the Shannon et al. Paper. Is all people from Leeds. I was very happy when they did this. So this is, shows the rate coefficient of this system here, OH plus methanol, which has a barrier, so it's not supposed to go at this low temperature, but actually because it is cold, and because in these low temperature environments, these two reactants can kind of stay together for, a bit longer than in warmer environment, the barrier can be overcome via tunneling, and this is why this rate coefficient is like much larger than what expected at this low temperature that they could measure. I mean, and this is still 60 Kelvin, so it'd be nice to go even lower and see what happened there. So anyway, there is a lot of new thing coming up for these molecules. And now, of course, we want to also compare what we see in space with what we have in the comets, and these many groups are working on this. Here, I am just showing a graph that comes from Beaver et al. This is work done with the 30-meter antenna, but there is also, of course, the paper by Altveg et al. With the 67P comet that was visited by Rosetta, where they also have this beautiful detection of glycine and many other molecules, including also phosphorus P-bearing molecules that, as you know, it's very important for our, say, DNA and RNA. So anyway, so this is the comparison with respect to methanol of various molecules that are measured in two comets here and two star-forming regions. Let's, for the moment, forget about the blue and green, but in general, with some notable exception, but in general, the abundances are, say, quite close to each other, considering how different these regions are, okay? So we talk about, just clouds of material and comets, so solid bodies in our solar system. And then, of course, there is the beautiful work by Karin that also showed here the detection. Well, this was the first detection of complex, say, of organics in disks. And the very nice thing is that if you take the ratio of these organics and you compare with what is found in comets, yes, you have very similar values. So again, it tells us that the solar system chemistry is not so unique, and you can make these probably almost everywhere, okay, in space. So I have a few more minutes, I think. Just checking. It's okay? Okay. So I wanted to then tell you a little bit about this work that I'm doing about these early phases of protoplanetary disk. So this was work that I started when I was in Leeds, and thanks to the collaboration with Aaron Boley and Richard Durisen, and also, of course, Thomas Hartquist, we were curious about these self-gravitating disks. And of course, we don't really know yet exactly how these disks are made. I mean, we have some ideas. Of course, you have a rotating cloud, magnetic fields, but that's the problem actually, because you have magnetic fields, you have ionized material, you can have actually coupling of ions with the magnetic field. You can have some angular momentum loss, and you can actually end up forming zero disk or no disk at all. And this is what has been seen in various simulations in the past. So you have really to tweak and change parameters to make your disk on the first place. I'm not talking even about, the evolution of later stages. So we started just to say, okay, fine, let's see if initially these disks are relatively massive compared to the protostar. In that case, one could expect to have these disks self-gravitating, forming some kind of spiral arms and basically shocks around these arms that could, of course, stir up the gas, make temperature going up and down, and these we could be able to then, say, measure with the telescope if this is the case or not, and at least answer the question, are disks initially self-gravitating or not, okay? So these are some of the maps that, so this was the original hydrocode after several orbits of the self-gravitating disk from Aaron Boley. Then we took it, we plug in some chemistry, and we have here images of water and H2CO, again showing nicely how different molecules can take different regions of these disks, which is also a nice prediction. This is the work by my student who is still in Leeds, that he actually took one of the a smaller disk, so considering a disk around a Proto-Solar young stellar object, and see if it could also develop, say, the spiral arms, what is the temperature, what is the basically the dynamics of this disk. And again, if you have the self-gravitating disks in these regions, even if the total mass of the disk here is only 0.17 solar masses, you can have quite a lot of excursions in temperature and variation. So here I'm showing the basically a fluid element, the orbit of a fluid element, and it shows here variation seen from above. So you see the disk here. And then if you look at John, you see this spike. So there is actually a lot of mixing in the disk. And when you have yellow, it means it's hot. It's about, say, here 80 Kelvin. If you are in the outer part of the disk. If you are in the inner part of the disk, the temperatures can go up to 500 Kelvin. I mean, it's a very high temperature. So again, you have a very zigzag-ish type of orbits here. And so you can imagine that you have lots of mixing. And if you do not form some pebbles, or where you can actually hide your eyes and say preserve your eyes from the prestellar phase, definitely, at least in this region here of the disk, you are not going to have much left there. So you have to start from scratch again. And I just noticed, recently there was this nice paper by John Tobin in Nature that actually showed that apparently this is the first example of this type of system. So gravitationally unstable disk, but that here has already formation of protostar inside. And finally, this is my last thing, is the work that is led by Zhao et al. In my group, that we are really looking into this problem of the protoplanetary disk formation. And because Bo started to include this chemistry in the non-ideal MHD code that he has, we wanted to track and at least follow as accurately as possible the ionization fraction. What he discovered is that actually you get something very interesting. So when you start the contraction of your cloud, you have probably the grain size distribution that is the MRN distribution, Mattis-Rampl-Norziek distribution. So you have say, grain size that goes from about 0.005 micrometer up to 2.5 micrometer with a certain power law, is a 3.5, and then we kind of started to play a little bit with that, because one expects that as molecules freeze out, maybe also small dust grains that can also be considered sometimes as the big molecules can also freeze out. And in fact, what happens is that if you get rid of the very small grains, so I mean those that between 10 and 100 angstrom, you have quite interesting effects in this non-ideal MHD, because then here the magnetic diffusivity, the one that basically regulates the ambipolar diffusion, so the slipping of neutral to, say, through magnetic field lines, it has a very large effects, because these small grains are tied to the magnetic field lines, so those are the ones who can actually get rid of the angular momentum and produce this magnetic braking. But otherwise, if you get rid of them, you have not such a problem, and you can form rotationally supported disks of tens of astronomical units in radius. And then you can make all the disk you want, because of course you can change parameters, you can change the cosmic ionization rate initially, you can change the density, the rotation, whatever, you know, and you can make large, big, with holes, with no holes. But the important thing is that you can make this protoplanetary disk. So I thought that this was worth showing. The other thing I wanted to show is that because of this freezing out, I think we should also take into account the fact that ISIS, of course, will also be enriched by these small grains, and maybe this could be, and this is just of course speculation because nobody knows, that this could be the precursor of the organic matter that is found in carbonaceous chondrites, like for example the IOM, the insoluble organic matter that resembles some kind of polycyclic aromatic hydrocarbon. I mean, it's much more complicated than that, but it resembled that. And then, of course, the even more interesting soluble organic matter that is made out of amino acids. And all of this material, both this and this, is, yes, highly deuterated. So it still kind of get some of this deuteration from probably the earlier phases. So I just want to go through these quickly, but just to make some points. So molecules are unique tracers of dynamics, and they have, of course, helped us since decades to understand the structure of these filaments and how these cores form, although there is still lots of work to do on this. Prestellar cores, these are dense cores where stars have not formed yet and have large densities. There is this critical value of the central densities that is 10 to the 5, which is exactly the dust-gas coupling, and apparently after you go beyond this point, it's very hard, say, to not let them contract. And this is what we see. There is a large amount of CO freeze out. There is a large amount of diffraction, 90% of CO in solid phase, okay? Even more, actually, in the center of this prestellar core is 99%. There is quasi-static contraction for the few cores that have been looked at, and formation, and probably also high storage, just put in parentheses because of comms that then can be delivered later. there is also this large diffraction in all phases of star formation. As we have seen, we see it from prestellar core down to Earth, basically, and this could be easy to explain if prestellar ices are stored. Even a fraction of them are stored, and of course processed later within pebbles and rocks. There is probably this new way to help the formation of protoplanetary disks, at least in our model, because protoplanetary disks, they know very well how to form. Depletion of very small grains that can enable the formation of disks, and this is important for two reasons. One, that you need to follow the microphysics, and this is the beauty of this, say, chemistry and processes that you need to follow for dynamics, and also it could enrich a lot the ice chemistry. The comps, so the complex organic molecules abundance are similar. We have seen this is work by Karin, and it fits into this picture here that solar system chemistry is not unique. And remember that we have more than 200 amino acids, and not just that, also fatty acids and nucleobases inside these carbonaceous chondrites, and that all of these have also large fraction of deuterium. So I would like to conclude here. I want to just show you a little bit the structure of my group in Munich. That is made out of observations, theory, and laboratory that just start to now give some of the first results. And then theory, we're working on physical processes, chemistry, and radiative transfer. And then I also wanted to show you some activity going on that is to link together our work of astronomers to much more complicated work done by biophysicists, but with the idea, and this is all people in Munich, there are of course many more people here that work on chemistry, theory, and experimental biophysics that is moving on, and hopefully we will try to collaborate finally together and understand the origins of life, at least make some progress, say, toward that. I don't say to solve the problem. So thank you very much.
Okay, great, thanks. Questions?
You're welcome.
Alyssa.
That was wonderful, Paolo. Thank you. So you had the graph that showed the particles going around the disk and the crazy temperature variation stuff. So what I'm wondering about is if you go back a couple of steps and scale to your core formation, you said you gave this number of 10 times the freefall time. And then I'm thinking, if you look at the movie that you and I have seen, the simulation of those core formations, all this crazy stuff that happens. So what happens to the ionization, the temperature, to the, like, are the models that are giving you the deuterium fraction and giving you things like 10 times the freefall time, are they right in the presence of all that, not just time or sort of the spatial illumination, ionization variability?
So you're talking about the earlier phases then. So yes, I mean, in the earlier phases, you see, we have this simplistic view that we have kind of spherically symmetric, and yes, we have some contraction motion, but the thing is that what we see there is quiescent anyway. You know very well the transition to coherence. But Goodman et al. Anyway, so that's these regions are indeed quiescent. So, but definitely you have cosmic rays that goes through, that they charge your grains. I was showing this morning, in fact, that they are very important in making, say, distribution of charges much different from what we naively assume in our chemical models. It's not anymore -1. We have all ranges between +2, 3 to minus several, and that can affect, for example, the dust dynamics, and can affect also some of the chemistry. We are just starting now to implement these features in the models, and because these are first of all, we have not much knowledge on the, on the dust itself, and also on the ice composition. So we are trying to go in that direction, but it will take some time. So maybe in a few years, I'll give you an answer.
You mentioned that for the relatively simple organic molecules, the concentration, if you will, in meteorites is within an order of magnitude or so of your prestellar disks
Yes.
or cores.
Core,
or whatever.
yeah.
What I'd like to know is whether, I'm sure you have done calculations for the amino acids that are found in meteorites and how they compare in relative density to the simpler ones in meteorites, how that ratio would go in prestellar cores, and whether you have any hope you within an order of magnitude or 5 orders of magnitude of detecting the
In the
amino
gas
acids.
phase, yes. Right, so there are of course measurements and the numbers associated with the concentration of amino acids, and this can change a lot depending on the type of meteorite that you have. So assuming
You were
that
talking about carbonaceous.
chondrites and also the primitive one, so I'm sure here there are much more experts than me. So, but the C1 or CI, sorry, and some other that show water, lots of water and also lots of organics. So the concentration is small, so it's going to be, say, hard to detect these amino acids in space. But we have done this exercise with the glycine because that at least is the simplest amino acid. So if we can bet on something, we can try.
Is it the most common in carbonaceous chondrites of the amino acids? Right?
That I cannot answer right away. Yeah, I should. Yeah, but it's definitely the one that requires fewer number of atoms.
Yes, I
Yeah.
appreciate that, but that
But
doesn't mean nature is
that
more
is-
complicated.
Yeah, you're right. Yeah, no, that's true. But so from our calculations, it seems that with this very sensitive observation, we should be able to detect by stacking, not really detecting the line, but stacking a certain frequency, we should be able to detect the glycine. So we have done this calculation for the glycine. We didn't do it for the more complex, and now, of course, we will do it. See, maybe we detect a bigger one. But it's really hard. You need to basically, yes, have also a bigger broadband kind of simultaneous observation. That is the best thing you can do. So you can try to get as many lines as possible and then do a proper stacking analysis. Work in progress.
Phil?
Paolo, one of the really interesting things about L1544 is that its central temperature is so low, according to the results that you showed,
Yeah.
down to like 6 Kelvin.
Yeah.
And I'm wondering whether that is an important feature in the evolution of star-forming core, or is it just, a fluke that happens to apply to this particular core and not necessarily does not necessarily occur in the thermal history of other cores?
Well, I think, in a sense, this is a little bit, we mentioned this in the papers on the 2 classes, of course. So it's I think it's more general than that. Of course, one should prove it. So I don't want to say things that need, of course, observations. We don't have many of these observations yet.
You have 1527.
Well, okay, but that is not as dense as 1544. In any case, I think what happened is that when you go, so assuming that you have like a normal interstellar radiation field, if you go dense enough that the gas-dust coupling takes over, you start this kind of runaway cooling of the dust, and so it could well be that at densities above 10 to the 5, I actually could expect to see this drop in temperature. And this drop in temperature that makes the cloud, from isothermal to actually having this gradient in temperature could affect, in a sense, the dynamics, because yes, it can make it more unstable and can trigger. So I think it's just that this dust-gas coupling density that is very important for the evolution, yes, of the core in general. I don't know if you want to say some more.
No, that's good.
Okay, good. Thank you.
Why aren't there more examples?
More examples. So there is N183 that has been studied, and also so there is this central temperature of 7 Kelvin that was found, not with interferometers. So maybe if you go to an interferometer, it can go even lower. The problem is that the ammonia, although, okay, you can go up to a point within the core, but ammonia is not the great tracer of the superdense regions, as you well know, because the critical density is not very large. So we need to, I think, get some other thermometer to go deeper and find. Maybe also with the ALMA, you see with the dust, if we can measure several wavelengths, we can actually, that was one of our points that we're trying to do, to look at the temperature of the dust in the center. But yeah, if you see some core that has larger than 10 to the 5 per cubic centimeter, then you start to see larger deuteration. That is also goes with the low temperature and lots of freeze out. So something happens when you reach that density.
Yeah. Ammonia is nice because it's more volatile and doesn't freeze out. Formaldehyde freezes out.
Which is that's another mystery, because the binding energy of ammonia is as large as that of water. So there is, of course, there must be some production in the gas phase that. Yeah.
I have a question. So you showed one slide about the measurement of water vapor column density.
Yes.
You backed out the total amount of water ice. So is that backing out model dependent? Like, do you have an assumption that the vapor is in some sort of equilibrium with ice?
So for this, we have, say, the models have considered like the evolution of the chemistry in a cloud, where you have gas and dust. So you have, collision of gas with the dust, freeze out, and the important point is the desorption. Because if you just let it go and not desorb the species, you basically end up with thick icy mantles and no molecules, except for H2, H2D+, helium plus, and some other things. So it's like early universe chemistry. But it's not really what we see. I mean, we see still quite a lot of molecules, including water. So there is this non-thermal desorption mechanism that is very important for the water, which is due to the cosmic rays, we believe, we think. So because we can reproduce this with the fact that cosmic rays both can, say, heat a bit the dust. Actually, this is not important for water because they're not able to heat it up at temperatures that are high enough for the water to desorb. But what they can do is that they can excite H2 molecules, and the H2 molecules cascade down, fluoresce, produce UV photons, and these UV photons photodesorb the water. This is what we think is going on. So it's a balance between, the freeze out and you need these cosmic rays. So this is actually telling us that there are cosmic rays also in these dense regions. We could try to put limits on that as well.
Do you have a question, maybe?
Yes, I did. From the get-go, your talk has been, as you said, about seeing a complex molecular chemistry now being discovered as the precursors of life. But is there any compelling observation that demonstrates that they're not postcursors of life of long ago in the universe?
Oh, that's fantastic. I like that. Okay. So you're saying something that was already there.
Long ago.
And maybe, it's just part of the dust, who knows?
Yes.
And then for some reason you have sputtering or vaporization of that. No, I have not thought about that, but it's, I don't know how to start with though, if I want to do that.
I suggest you start with the following. It's been found that the 2300 angstrom bump in the interstellar curve, which is extremely universal,
Yes.
is probably the result of something like buckyballs. And we talk about the interstellar dust being made of paracyclic,
polycyclic
PAHs,
Okay.
polycyclic aromatic hydrocarbons.
hydrocarbons.
And from my work with Adolf Witt, we found they're devilishly difficult to make in a laboratory, but plants make them easily and commonly.
Yes.
All right,
That's a good place to start.
Good suggestion. All right, let's thank Colin.